All right, welcome back, y'all. I hope everybody's having a great day. We're going to learn about simple pendulums, okay? Now, the key about simple pendulums, we have to understand that they are ideal bodies that consist of a light extension cord, all right? And so that's what you have here for this L here, that purple line. One end in which is attached to a fixed O, right? And a small mass called the pendulum bob. And that's what this little bad boy is right here, okay? And so when it's on a pendulum bob and you have that pendulum bob, this is attached to the other end. When at rest, the bob hangs at the equilibrium position, currently right here. When pulled aside to the amplitude position and released from rest, right, we know that it travels a arc length x, right? We see that there through the equilibrium position to the amplitude. And so we have what we call some type of harmonic motion, okay? So we know when we're graphing sine or cosine waves, all right, we know that a wave has an amplitude, it has a crest, it has a trough, and depending on whatever that amplitude is, whether if it's positive A or negative A, we know that that amplitude is probably going to be at this point here, right? Because it's at its max. And then we see that the pendulum is then going to come back, turn around, right? Because we have gravity, which is pulling down always. And that is what we have here. Okay. And so we know that gravity is mass times the acceleration due to gravity on Earth. All right, we know that is 9.8 meters per second squared. And so as the wave or the harmonic motion is changing its position, all right, it goes from that amplitude and then it comes back down. And then you can just imagine what is happening in the graph, okay? And what is happening with this physical phenomenon. So we have the amplitude point. Okay, so that's where we have our max. We have the equilibrium position. Okay, and we have the arc length, which is pretty much the path that the pendulum travels. And the arc length is just is pretty much the crust of the pizza, right? It is this part here that length because it's curved that we call that arc length. Okay, and so a pendulum, we see the force acting on the pendulum as the weight. We also have a tension force, right? Because Newton's third law says every action has an equal and opposite reaction. So then we also have tension going in the opposite direction, right? And so with that being said, we have a force and we have these components. So if we break down these components, so let's say we have our XY plane. All right, and what I'm going to do is I'm going to literally just rotate what is happening. All right, and in physics, sometimes we have to change the orientation so we can better visualize what is actually happening with each vector, what's happening with each force. You understand? And so we have our X and Y plane. Okay, and we see that we have gravity pointing down, okay? But we also have this component here. So we know that if we zoom in a little bit, we see that this pendulum is moving two-dimensionally, okay, right? And that means that it's moving at an angle. And in physics, we use theta to represent that angle, okay? And if we extend out the triangle just a little bit, just so we can see it, all right? So let's say that it's just a little bit that, the gravity always pulls you down no matter what angle you're at, right? But what that means essentially is that you have not only gravity pulling you down, you also have it pulling you in the